shall we get started? Okay, so I mean, after the last hour, I hope that we're in agreement that this is a fairly complicated problem and that requires an enormous amount of inputs and with a lot of problems of inconsistent timescales and length scales, and where the different process, whether it is convection, conduction, radiation, chemical kinetics, transport, you know, all these problems, they all have a relevance, and that relevance is defined by the boundary conditions. So you cannot get rid of the boundary conditions. The problem can only be solved in its integrity. So the characteristic length scale of the domain is generally many, many orders of magnitude bigger than the characteristic length scale of the mesh that is dominated by the smallest time scale. So computational cost is extraordinary. Now also, this is a dirty problem. So effectively the scale of the problem and the nature of what is happening makes diagnostics extraordinarily difficult. So the resolution and the quality of the measurements that you're taking is quite difficult to match with the precision that is necessary. And therefore, you know, the treatment of tools like AI in this type of problem is actually quite tricky. Now, needless to say, if you move to the space of, for example, forest fires, where now your scales are in the orders of kilometers, and your fluid mechanics is of the complexity of atmospheric fluid mechanics, you know, and combined with all the same things that I've put in the board here, then the problem becomes quite intractable, okay? So we need to keep all these things in mind, because in contrast, what we need is actually very simple and very coarse, okay? Because the error bars of my required safe egress time of my RSER are so big that the resolution that I need for this is actually quite low. So I can take advantage of the fact that I don't need precision to be able to try to solve the problem in a simpler way, okay? So what I'm going to try to do first is clarify a few misconceptions, you know, that it's important that I make very clear. And then I'm going to go into a framework, which is the compartment fire framework, you know, which is a framework that was developed in the 1970s that basically addressed the need in the context of the tools at the time. And they proposed a way to simplify things so that you could actually create a design methodology that you could use for the purpose of delivering fire-safe buildings. Is that okay? So the first thing is we need to recognize the difference between a fire and an explosion, okay? And there's a number of different elements to this and reasons why this is very important, because in a way it represents the ultimate goal. Now, when you're thinking of a problem, this is the Texas City refinery, and there was a major explosion about 15 years ago that created an enormous amount of damage and killed a number of people. And this is a very common scenario, you know, when you're dealing with explosions, that you're going to have this major event, and this major event is one that is going to be resulting in the deaths of a number of people. Now, the obvious difference is that, of course, when you're talking about an explosion, you're talking about a premixed flames, what a fire is a non-premixed flame. Is that okay? Now, that has a number of different implications, but the most important implication is when you have a premixed flame, you know, and that premixed flame can propagate in the gas phase. And as it propagates in the gas phase, if it does it fast enough, then you're going to create a pressure wave, and yeah, that's a result of the transition from a deflagration to an explosion, and potentially you're going to start creating chemistry in front of the shock wave, and that is a detonation. So you can actually go through the whole range. Is that okay? Now, in the case of a fire, that will never happen. A fire being a non-premixed flame, it requires for the fuel and oxidizer to converge in a certain place. And because of that, there is no propagation. The only propagation is the spread on the condensed fuel. So you have to heat and pyrolyze the condensed fuel for the fire to be able to progress. So the only motion is determined by the engagement between the heat being generated by the flame, heating the solid and producing new fuel that eventually allows the flame to spread. But in essence, the flame chemistry doesn't move because it's defined by the location where fuel and oxidizer get to the reaction zone. Okay? So in that sense, they're very different, and the characteristics of a premixed flame and a non-premixed flame determine completely different problems. Now, we are not going to address explosions, but nevertheless, the key thing when it comes to explosions is that your available safe egress time is 0. Okay? So all these calculations that we need for fire, which are consistent with the fact that I need to calculate the available safe egress time, they're pointless here. Because it's going to be so short that, in essence, you will not have any time. So the way we deal with explosions is fundamentally through prevention. An explosion cannot happen, okay? And full stop. So you put all sorts of prevention rules to try to mitigate the probability of an explosion to a level where it becomes acceptable, okay? So in essence, there are two completely different problems, and the fire problem is a much more complicated problem because it requires the creation of this fire safety strategy that is based on the idea of assessing characteristic times, okay? While in the case of explosions, the issue is mostly trying to create a procedure of management that mitigates the probability of having the event, okay? So very, very different problems, so that's the first thing I wanted to clarify. So here you can see the case where the two of them converge. So if you look at this video, this is a video of a fire and the phenomena that is known as backdraft, okay? So what is this phenomena? So effectively you have a fire and the windows have not broken, and so the containment is an enclosure, so eventually the fuel is going to consume, all the oxygen. And as the fuel consumes all the oxygen, the flame extinguishes, but nevertheless the compartment is still very hot, so fuel is still being produced, so you end up with a compartment filled with extraordinarily hot gaseous combustible gases, okay? So what is going to happen here is that the firefighters, as they're trying to fight the fire from the top, they're going to perforate the roof, and they're going to create the possibility of fresh air, a current of fresh air, getting into this compartment that is fuel rich. So turbulent mixing is going to result in a significant area of pre-mixed conditions that is going to allow a flame to spread through the compartment, and you get the backdraft. God. Okay? So that is the only scenario where basically a deflagration coexists with a fire, where you actually have a non-premixed flame eventually extinguishing and leading to conditions that you end up with a premixed flame. And that phenomena is a phenomena that firefighters fear because it's so sudden and so dramatic, and of course can result in massive harm to the firefighters. Now, instead, the diffusion flame, effectively what we have is air in the surroundings. You have heat feedback that is going to go to the surface, and products of combustion that are going to emerge due to buoyancy on the upper part of the flame. So fuel and oxidizer are separate, and fuel is controlled by, the production of fuel is controlled by heat feedback. So the feedback loop from the gas phase to the solid phase is unavoidable. Okay, so you have to resolve that feedback loop to be able to create the fuel that you need, to produce. And of course, the moment that you get a flame, then buoyancy takes over, and what you get is natural convection, and you get buoyant entrainment, and effectively that's what feeds, the fire. So, in essence, that's the problem. So if you look at a candle, and where is it here? So, and this is a video, but you can see that when it's laminar, and it's sort of a very, very, very small candle, effectively is motionless. So you can see the candle looks almost static, despite the fact that what you're watching is a video. And effectively, here is the flame sheet, and it goes all the way around. Now, how does a candle work? Effectively, what you have is a wick, and the wick allows, due to capillarity, for this molten wax to be raised, increasing the surface to volume ratio, okay? So the wick, the only purpose of the wick is to increase the surface to volume ratio, okay? So because you have a larger surface to volume ratio, the heat from the flame evaporates the fuel which is in the wick, and the fuel then starts migrating upwards until eventually starts the whole sequence of cracking until you get soot production, and then the soot gets oxidized, and that's the glowing that you see, and eventually what gets out of the tip is effectively CO2 and H2O, okay? So the whole thing, has burned. Now, does anybody know how do we design a wick? That was the wick was first designed by the Egyptians, so it's several thousand years old, and it's an extraordinarily smart and practical device that the Egyptians created without really understanding exactly what they were doing, but observationally understood the concept of the smoke point, okay? So what happens? So if I increase the size of the wick and make it longer and longer and longer, then the surface is increasing, so the amount of fuel that is being gasified is going to continue to increase as you increase the size of the wick. Is that okay? So if I'm consuming the wax, the wick is getting bigger and bigger and bigger and bigger. So in essence, if you have a wick that is poorly designed, it's going to start increasing in length. And as it starts increasing in length, it's producing more and more fuel. And as it's producing more and more fuel, eventually that fuel is going to be so far away from the wick before it gets consumed that it is going to be contributing to the combustion at a very, very low rate. So the fuel is being diffused into the flame at a very low rate, which results in a low flame temperature, which eventually ends up quenching the flame at the tip. And the moment it gets quenched at the tip, you get soot that emerges at the top of the flame. That's called the smoke point. And because that soot that emerges at the top of the flame then gets deposited in the ceilings, people used to have houses with black ceilings, okay? And to prevent that, they constructed the wick. Now, how they constructed the wick? They used two different types of fiber, one that expands more and one that expands less. So as the wick starts growing and it heats up, the inner fiber expands less, the outer fiber expands more, and the wick curls. And the moment the wick curls, the tip of the wick is going to touch the flame sheet. And it gets consumed systematically, keeping the wick always exactly the same size. And by keeping the wick exactly the same size, your flame remains below the smoke point, and as a result, you get no smoke getting to your ceiling. Pretty smart, no? Very, 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 very simple approach, but effectively one that addresses very fundamental problems that we need to understand. So the real question is, and I talked about the smoke point, why do fires produce black smoke? Huh? I mean, that is the evidence. So it's unburned hydrocarbons. But why do fires produce unburned hydrocarbons? Yes, it is a trick question. So why? Why do fires produce unburned hydrocarbons?
Unburned carbon. The hydrocarbon can break down, make carbon.
You have, yeah, yes.
Reaction, probably because it doesn't get hot enough to ignite the particulate carbon.
But it does, because if you look at the bottom part, you can see the glowing, and this is effectively that. What it is is oxidizing soot, no? That's what glows with a broad spectrum.
It's oxidizing soot plus the other gases that pyrolyze down.
Yes, I mean, yes, okay? So in essence, when you get broadband emission, it's generally the oxidation of the soot, okay? That's what gives you the broadband emissions. All the other stages of the chemistry are going to give you narrow spectra, you know, because it's gas to gas, okay? While the soot particles are going to glow before they get oxidized, and that's what you see here as broadband emissions. But why do we get black smoke? Huh? Well, you see, this is a misconception. Everybody thinks that it's because fuel-rich, but the reality is that the entrainment is more or less 10 times stoichiometric. So actually what you have here is fuel very lean.
Yeah, and therefore, the temperature is far below the adiabatic flame temperature. And again, it won't ignite the particulate carbon.
Yeah, so it has to do with temperature, because effectively the particles cannot ignite. Okay, so at some point, what ends up happening is that your temperature gets too low, and then the carbon doesn't ignite. And as a result, it comes out as non-combusted carbon. Okay, now, so people think, and generally this is a very, very strong misconception, that when we're talking about fires, we're going to have fires that they are fuel-rich and fuel-lean. Okay, but that's not the case. All fires are fuel-lean in general. Only at very, very later stages and very unique conditions, they become potentially fuel-rich. But the reality is that fires are all generally fuel-lean in the sense that they have plenty of air. But the chemistry happens, like in all non-premixed flames, where at the location where fuel and oxidizer are delivered in stoichiometric conditions. So actually the combustion itself is stoichiometric. Okay, so this fire is actually burning under stoichiometric conditions, and the only reason why you get the soot production is because you get flame quenching. And is exactly the same as the smoke point. There's a very famous paper by this man called John DeRis, and basically he tries to create a mechanism to introduce quenching into CFD models to be able to predict soot production from a purely thermal way without having to use any chemistry. Because if you identify a critical temperature below which you get flame quenching, then you identify the smoke point. So by doing experiments with small jets, and depending on the different fuels, they characterize the condition that leads to quenching, which is the condition that leads to the smoke point. And as a function of that, then you can establish the moment where combustion ceases to occur. And the result is that all the fuel in gas phase that remains then now comes out uncombusted. And it comes out uncombusted not because it's fuel-rich, but because it has quenched. Now, from the perspective of numerical modeling, that is a real problem, because being able to model the quenching of the chemistry is extraordinarily complex. So you have to find a surrogate that is simpler than modeling the quenching of the chemistry, and that surrogate appears to be this smoke point temperature. So that is a possibility. Now, it hasn't gone very far for a number of different reasons, but it is, again, one of those concepts of simplification that is really fundamental to try to understand how we can model something that otherwise cannot be modeled, okay? But in essence, the black smoke here is simply because the flame got too cold, okay? That's the reason why you get black smoke, and it is not because it is fuel-rich, okay? So, and you can tell that by just looking at Berg-Schumann. So I took those diagrams from a previous summer school lectures by Moshe Matalon, but it's just a reproduction of the Berg-Schumann solution, okay? The Berg-Schumann solution basically assumes that the flame is an infinitely thin sheet, and that infinitely thin sheet results in no fuel in the oxidizer side, so there will be no fuel in this side, and no oxidizer in the fuel side. Everything gets consumed at the flame location, okay? So the flame location is XF, and that's where you have no fuel and no oxidizer. So basically the two mass fractions go to 0. Now, these are the normalization parameters. So this here is the global equivalence ratio. It's a mass equivalence ratio because these are the molecular weights, and this is the stoichiometric coefficients, and this is the initial fuel concentration at the base of the burner, and this is the initial oxygen concentration at the base of the burner, okay? So this is the mixture fraction, basically, a mass mixture fraction, and here you have the Schwab-Seldovich variable, just the traditional way of solving the mass equation, so the standard equation with a normalized variable, and that leads you to this solution, which is a Bessel function. So this is the first term of the Bessel function, and these are the nth term of the base. Well, it's a Taylor series that every term is a Bessel function. Okay. So, I mean, this is a classic 1926 paper. Yeah, everybody has heard of Berg-Schumann, so I'm not going to get into the details of how you get this. You can find this in every textbook. But the reason why I wanted to show that is because the Berg-Schumann solution carries a term C. And that term C basically is the ratio between the diameter of the fuel and the diameter of the oxidizer co-flow. And basically determines the ratio that you have of available fuel and available oxidizer. And what Berg-Schumann concluded by analyzing this problem in this term and making this assumption of the flame sheet approximation is that effectively there's two types of flames. So all flames, you can characterize where the flame is going to be, and this is a solution for the position of the flame, but depending on the value of C, or the value of basically the value of C, you will get two types of flames. A closed flame, okay, where effectively the fuel gets consumed at the axis of symmetry, or you get the tulip flame, where the actual fuel is consumed, basically the oxidizer is consumed at the wall of the oxidizer co-flow. Okay? Now, in both cases, you're assuming infinite chemistry, so there is no quenching. So in this particular case, what you get is just simply the location of the flame. Now, this is in essence what is at the core of a diffusion flame. As you change the parameters, you change the fuel and oxidizer supply. What changes is the position of the flame. But the flame is always stoichiometric. Okay, so the flame is always going to burn where the probability of collision is highest, and that's where you get the perfect mixture of fuel and oxidizer. Okay, that's just purely Stefan Boltzmann. Okay, so in essence, what you have is just simply that the flame is always given by exactly where you get the appropriate supply of fuel and oxidizer. So in essence, what we're dealing with is a flame that is defined by its position. So if I decrease the amount of oxygen, what happens? The flame moves out. If I decrease the amount of fuel, the flame moves in. Okay? And then it becomes static and it gets placed in there, and it's always stoichiometric. So the only way to justify the production of incomplete combustion is if you break down the flame sheet approximation, where you get finite chemistry, and eventually the flame starts breaking at some point. Now, most flames, like in the case of fires, because they have oxygen in excess, they're going to be closed flames, and they're not going to be tulip flames. You can forcefully create these tulip flames, but in general, most fires, because of buoyant entrainment, are going to have excess oxygen, and therefore the fuel consumption is going to happen at the axis of symmetry of the duct. Okay? Is that okay then? Okay, so this is a very, very important concept that we need to be very careful that we understand, and we stop thinking that diffusion flames can be rich or lean. The concept of an equivalence ratio, when it comes to diffusion flames or compartment fires or any of these things is actually a surrogate. It is not a real concept that pertains to the flame. It is a concept that gives you a sense whether your flame is going to be here or is going to be there, but it is not affecting the actual chemistry of the flame. Okay? So if you look at these experiments that were done by Mikovsky a few years ago, you can see the different types of measurements, and you can identify how the flame moves, from a condition that is below the smoke point. You can see how the soot is being produced, the OH radicals go all the way to the tip, and eventually what you get is total fuel consumption. Now, in contrast, when you allow, by changing in this case, you get the oxidizer in the middle, and you get the fuel on the outside. Basically, you allow an excess fuel, so the fuel goes so far that eventually it is going to quench. And what you get is these open tip flames, where in the areas where there is no chemistry, you will get fuel that just simply escapes, to the outside. So by playing with the fuel and oxidizer and putting them in different places, you can either create these closed flames and bring them to the smoke point, or start with flames that are here past the smoke point and bring them here, to a condition in which, again, these are all always past the smoke point, so you have a quenching point, in here. So people have done these experiments, have done plenty of measurements of it, and it's very, very clear what the dynamic is. Eventually, you get to a point that you get quenching at the tip, and quenching at the tip basically eliminates the chemistry, and the moment it eliminates the chemistry, then you get unburned fuel coming out, and that's what effectively is the black smoke of a fire. So now let me show you a real fire. So this is a video that was created by NIST many years ago, and the purpose of this video was to show how effective sprinklers are. And so they compared 2 bedrooms, dormitories, college dormitories, 1 sprinkler and 1 non-sprinkler. And just a matter of warning, this is the ideal scenario for a sprinkler to actually work. So there's nothing more effective than that. So in a way, you're going to see a massive difference between one and the other. So basically, you get the ignition of the fire. At the beginning, you're going to get this sort of white smoke, but then the white smoke disappears because this little fire is away from the quenching space. So you can see there's barely any smoke, is more or less transparent. And the fire is going to start growing and getting taller and taller and further away from the surface that is evaporating. So the surface that is pyrolyzing the fuel, as the flame height increases in length, is going to be further and further away from the tip of the flame until it gets to a point where it's so far away that the supply of fuel is so slow that then the temperature drops down and the flame quenches at the tip, and you get an area of quenching, and that's when the black smoke starts appearing in higher and higher quantities. So at this point, you're already seeing a little bit of that black smoke coming in. And look at the time scales. So you can see you can have this initial period of incubation is about almost 2 minutes, in which still, this room is somehow tenable. Now, one of the really important things is to make a decision of what tenable is and what tenable is not. So if I stop the video here and I ask you the question, would you be comfortable inside that room? Okay, that's where it's getting to a point where maybe not, no? Would you be dead inside that room? No, you're still fine, no? So this is where we start getting into the decision making. So we were talking earlier, where do you set the threshold? So there's a number of things that you have to take into consideration, because if an individual perceives that the hazard is imminent, that tends to lead to panic, okay? So in essence, the moment that the behavior of an individual is a panic behavior, then all your calculations go out of the window, okay? Because you cannot predict at all the behavior of an individual in panic. Is that okay? So a first threshold is to consider how big of a fire do you think will still allow a person to remain somehow conscious that they're not at risk, so that they can actually walk in an appropriate way and perform the appropriate decisions that are far away from panic. Now, you can bring it, if you want, and be less conservative, basically ignore, assume that people have left already by their own, okay? And you can assume that your threshold might be actually the threshold where you actually have harm, okay? And you can define it in multiple ways. You could define it in terms of how big of a size of a fire makes you comfortable. You could define it as a threshold temperature at the ceiling level. You could define it as the, because the smoke accumulates in the top, the smoke layer not having descended to head height, okay? You can make whatever assumption you want, but you have to be explicit and you have to have a rational justification for it. Some people define tenability as a function of visibility. And they will say once you lost 10% of the visibility, in other words, you've absorbed 10% of the light, then people start believing that, and they've done a lot of experiments with people, that you stop seeing the signs. So in a way, you could define it that way, but this is where you start thinking of what the threshold is. So at this point, and this is about almost 2 minutes, this is where we start becoming uncomfortable, okay? So it is very clear that at this point, people more or less better be out, okay? If you push it too far from here, you're really playing with fire, okay? You don't want to do that. Is that okay? So then let me ask you a question. Have the sprinklers activated? No, have they activated at this point? No, they haven't activated. So if the sprinklers have not activated, and I already want everybody out, can I consider the sprinkler a life safety provision? No, because basically the sprinkler is going to activate after everybody left. Is that okay? So the sprinklers are not life safety provision, they're property protection provisions, okay? They're not going to increase the chances of people from evacuating, okay? The only thing that they're going to do is basically stop the problem before you get too much damage. So it's a property protection provision, yeah.
What if someone's like passed out?
You can never design for stupidity, okay? But that is a principle, okay? So the outliers, sorry, I mean, there's certain things you cannot do, and when we design, we always have to consider, being all-encompassing, all-inclusive, but there is a point where you have to cut the tail, okay? And there's certain things you cannot decide. And I agree with you that if somebody's passed out on the bed, maybe you can argue that the sprinkler might have saved them, but it is very likely that by then they will probably be dead anyway, okay? And so if I let this, continue, then you can start seeing how the smoke layer now is beginning to descend, and you can see how the obscuration at the top is quite significant. From this angle, you cannot see it. Then the sprinklers eventually activate, and then the fire is still small enough that the sprinklers are going to suppress the fire. So the image on the top right is going to disappear. So then the fire continues to progress. It's getting bigger and bigger and bigger, and the smoke layer continues to descend, and you're going to see how it's getting darker and darker and darker. Not only is it getting darker, but you will start seeing the papers in the books, basically start pyrolyzing and eventually igniting. So the temperature of the smoke layer then becomes significant enough that it can actually ignite the paper. Now, at some point, the camera gets fried, so you cannot see any further, and they only have to look at it from the outside. So in essence, what ends up happening is that as the smoke layer descends, okay, and basically fills with hot gases the top, it starts affecting buoyancy. So if you think of a system like this, where you're going to have stratification, the top is now hot, okay? And if the buoyant plume wants to get into the smoke layer, it can't anymore because buoyancy gets neutralized, not because all this is hot, okay? So it doesn't have the strength to penetrate this. So in essence, what you're doing is lowering the ceiling. So you're getting a fire that is getting bigger and bigger and bigger, and because it's getting bigger and bigger and bigger, okay, it is producing more and more and more fuel, and the smoke layer is bringing it down. So the fire starts opening up because it starts moving towards the oxygen that is less and less and less. So your flame starts getting fatter. So the moment your flame starts getting fatter and the convergence of the tip of the flame with the smoke layer results in a tulip type of flame, then eventually you start getting more and more products of unburned combustion that are getting into the smoke layer, and the flames actually get started to be deflected, you know, to the actual lower surface of the smoke layer, okay? So basically you're getting more and more and more products of combustion, of incomplete combustion, that are basically filling these hot gases, and that's purely fluid mechanics. It's basically Burke-Schumann. So you're moving from a closed flame into a tulip flame, okay? So, and you can see how fat the flame is already. It's completely opened up. And you can see the obscuration at the core, because here's where the unburnt fuel is just literally getting in, entering directly, you know, the smoke layer. Now, eventually, that smoke layer is going to get so hot that the radiation that it produces starts igniting all the combustible surfaces wherever there is a combustible surface. And then you get a point where everything ignites simultaneously, and that's what we call flashover. Okay? Now, once everything ignites simultaneously, the amount of fuel that you are producing is astronomical. What is the flame then going to do? If it cannot go anywhere, what is going to happen? It quenches, and then this is where you get the risk of backdraft, okay, what you saw in the previous video. But what really happens is that it will migrate to where there's oxygen because it's a diffusion flame, so it has to go to the place where the two of them are in stoichiometric, and that is in the door and in the window. So in this case, they left the door open, so that allows air to be entrained, and the flame is going to be placed at the interface between the fuel and the oxidizer, okay? Now, the other place where it happens is at the window. So at this point, the windows are still intact, and therefore flames cannot happen in here. And you can see the black unburned smoke happening in there. And the flame is burning because you're getting air entrainment at the bottom of the door that is open. So you have these flames at the bottom of the floor because you're getting air from the bottom, and then all the top part is basically filled up with products of incomplete combustion. Okay? Now, eventually, the glass panes start breaking, and as soon as the glass panes start breaking, the flames displace themselves to where oxygen is, and then you get a flame, a diffusion flame emerging at the window, and that's the spill plume, you know, and what we call the spill plume. And you can see it already happening here. As soon as there's a hole, the flame appears in the corner. Okay? So eventually you're going to see the glass pane falling off completely. There it goes. And as soon as the glass pane falls off, you can see the flame is at the surface. Okay? Now, the more glass panes I break, the more air can come in, and therefore the greater intensity of combustion, because you have plenty of fuel, and the more air you get the more surface that is actually combusting. Now, this is what brings us to that ventilation factor that you were talking about. So depending on the geometry of the compartment and the size of the openings, you're going to get more or less flame. So if you have a massive compartment, okay, with windows only at the edges, most of the compartment is not going to be burning. Okay? It's going to be filled with products of incomplete combustion, but the flame is only going to happen at the edges. So the average temperature of that compartment is going to be very low because most of it is not burning. Now shrink the compartment and make it a cube and put doors and windows around it where air can come in from all directions. Then effectively what you get is a lot of burning. And in that case, then you're going to get, on average, higher temperatures. Okay? Now, if now you put glazing all over the place and you get so much air coming in, it starts cooling down because you have too much air supply, the flame starts migrating inwards, and then the average temperature again goes down because of the amount of air that you have. Okay? So, as you can see, when all the panes break, then you can see all these flames burning outside, and that's where they're finding the oxygen. And obviously, because the surface area of oxygen, of air now is bigger, then obviously the intensity appears to be higher. So, post-fire assessment, that's the success of a sprinkler when it works. It kills the fire in its very incipient stages, and your property has been protected. Okay? So it's a massive benefit when it comes to property protection. Okay? Now, the case of non-sprinkler, this is designed for burnout. Okay? So as you can see, you've consumed almost all the fuel, despite the fact that there's something left in there, but you've consumed pretty much all the fuel, and the structure is still intact because this particular structure was designed to withstand the burnout of all the fuel. Okay? So that's a real fire, and that's how fires normally look, but as you can see, they're governed by exactly the same rules. Okay, so it's no different to a Berg-Schumann. It's just a lot more complicated because the fuel source is more complicated, ventilation source is more complicated, and the length scale creates turbulence. And the moment that you have turbulence, then you get all these very complicated eddies, and those need to be predicted. But in essence, it is fundamentally the same as a Berg-Schumann problem. Okay? So a compartment fire going from the completely ventilated to the completely under-ventilated, if you want to call it that way, is basically the Berg-Schumann going from this to this. Okay? So, now, if you look at it in actually quantitative terms, you get the point of ignition, and at the beginning, you will see that the temperatures grow very little, and you get your smoke alarm happening very early, then the beginning of obscuration, so that the smoke, the haze, starts being produced at the top, and at some point, somewhere around 5 or 6 minutes after ignition for a compartment of that nature, then the temperatures start increasing quite rapidly until you transition to this flashover where everything ignites, and then the temperatures remain fairly high, and in this case, your temperatures are about 700 degrees Celsius. Okay? So that's the temperatures. So as you can see, in the earlier stages, the room has excess air, so the flame is closed, okay? It has excess air, but as the fire gets bigger, then you start not being able to supply sufficient air to the room, so the flames start changing their shape, and they start becoming a tulip and producing now much higher levels of carbon monoxide, much higher levels of hydrogen cyanide, and all these actually negative components. And eventually, the oxygen inside the compartment goes to zero, and at that point is where you get the flame only burning at the opening. So the flame has displaced itself in a place where it can react at stoichiometric conditions. Okay? Now, needless to say, the flames on the outside have a lot less soot than the flames inside. Why? Because you have the supply of fuel that is limited by the size of the opening and an enormous amount of air that can be entrained, so the flame closes again. And what you get with this shape, as you can see here, basically it closes and all the fuel gets consumed somewhere around the tip, okay? So in essence, what is important here, first is the transition, which is flashover, normally about 4 or 5 minutes into the fire. And it's in this period before flashover that you need to define your TF. Now, if I define TF as the time to flash over, I'm a criminal, okay? Let's just face it, because I'm going to kill everybody. Is that clear? So I have to define my TF a lot earlier than that. Now, where am I going to put it? Wherever I think the level of conservatism is appropriate. So you can use criteria of obscuration. Sprinkler activation, I think, is too late because everything is accelerating at that point. So it will be dangerous to get people still in the place while everything begins to accelerate. You know, you probably want to go somewhere here, you know, where it's flat, and you still have plenty of time available in case something goes wrong to capture those error bars associated to the people's behavior, okay? So in essence, that's kind of what it is. Now, how have we framed this? So basically, the way in which we frame the problem, and now I'm simplifying, okay? Everything that pertains life safety or up to sprinkler activation, I am going to consider it in this particular space, okay? But I'm going to split the problem and say once you get post-flashover, the only thing that I'm going to address is the structural behavior. Why? Because now the temperatures are high enough to be able to affect the structure, okay? While here, the temperatures are too low to have any impact on the structural behavior, so I can ignore any structural deterioration in this period and focus entirely on all the protection measures in all the fire protection that I'm going to put into the system. So instead of treating this problem as one single problem that addresses all these components, I split it in half. And I said, when it comes to evacuation, alarms, sprinkler activation, and all these things, I am going to talk about pre-flashover fires, okay? I'm going to treat them as a function of a two-zone model. So I'm going to split the room in two. The top part is smoke, and the bottom part is air, okay? And as soon as I get to flashover, I start all over again. I put all my fuel. I make it all burn simultaneously, okay? So basically, the entire floor is burning. I treat the compartment as a compartment that is full of products of combustion, and burning is only happening on the outside. And as a result, I have a single zone model. So effectively, I've created one single volume. And this is the problem that I'm going to be solving when it comes to addressing structures. Why? Because now the temperatures are very high, so heat transfer to the structure becomes important because it starts deteriorating the behavior of all the construction materials. So in essence, now I'm working with two problems, not with one. And I'm splitting them completely, and I will address them as if they were completely different problems. So if I want to address the structure, I do the post-flashover, fully developed fire. If I want to address everything else, I'm going to do the two-zone model, you know, pre-flashover fire, okay? So that's my first simplification. I split the problem in two, okay? So I have now two problems to work with, and I'm going to work first with this one, and then I'll work with the second one. So the main aspect that you need to address when you're dealing with pre-flashover fires is what happens with this when the smoke accumulates. So if I take these images and I put a video of the chimney, so what's the difference between a chimney that works well and a chimney that doesn't work? Yeah, so the smoke doesn't go up the chimney. Is that okay? So in essence, the reason why a chimney is safe in your home is because the problem is a steady state problem. Why is a steady state problem? Because all the hot gases get evacuated, okay? So if your chimney is not working properly, what ends up happening is that all the gases don't get evacuated, so then the smoke gets accumulated or the heat gets accumulated, and then it gets spilled into the compartment, and that becomes very dangerous, okay? The chimney is not doing its job, okay? Now, in contrast, if I now create a compartment and I burn the fuel in the bottom, then the process is transient. Why is it transient? Because I'm not evacuating the smoke fast enough. So what the smoke is doing, so I'm burning, the smoke is going to the top, is heating the ceiling first, and producing a smoke layer. Now, to accelerate the process, I put a piece of material here to start accumulating the smoke. But you can see how the smoke accumulates and produces a smoke layer, and that smoke layer is going to start getting darker and darker and darker. As it gets darker, its emissivity increases, radiative feedback starts increasing, and because radiative feedback increasing, the burning rate starts increasing, and as the burning rate increases, more smoke and heat gets produced, the smoke layer becomes hotter, and then radiates more, and it becomes an acceleratory process. And that acceleratory process eventually radiates so much that you will see these pieces of timber igniting, and that's the moment that you get flashover. So there they ignite, and at that point you get fuel being produced in the entire surface. It's too much fuel, so the fire moves, or the flames move to the outside, and what you get is your diffusion flame establishing externally to the compartment. Now, a compartment fire that allows for the smoke to accumulate, effectively what it's doing is creating a transient process that inevitably ends up in something like flashover. Now, of course, if I open too many windows and I aerate everything, I might never reach flashover because it will reach a steady state, okay? And it will become basically the same as a chimney. But normally, most compartments, they don't have that capacity to vent everything, so eventually the process remains transient until eventually it reaches flashover. The moment it reaches flashover, I don't need to do anything else because I'm moving to the other problem, and I'm going to treat the other problem in a different way, okay? So to make my decision on TF, the first thing that I need to understand is what is the time to flashover. And then I will define my available safe egress time as a fraction of that TF, okay? So if the time to flashover is 5 minutes, I might define my available safe egress time as 20% of that and say it's 1 minute, or 30% of that and say it's 2 minutes, or 1 minute and a half. Is that okay? So, but the reference point is the time to flashover. So that's what I'm going to try to calculate, and then I will make a decision how conservative I go, okay? How much time I leave, for people. So it's almost 3:15. Let me see what's next. No, let's go on a break for 10 minutes, and then I'll pick up from here, okay?